not immediately, a few years afterwards, there was this very strong graduate student in applied math working with Andy Maida. And this strong graduate student went from, let's see, from Princeton to Chicago as a Dixon to Duke, then was stolen by UCLA, right? And has played in partial differential equations and fluid flows, and also in agent-based models that have to do with crime and order, and also in farming, and has gone on to get all kinds of distinctions, including the Kovalevsky Prize. But again, I remember this student that was working with Andy Maida when I started, so welcome.
Thank you, Giannis. Actually, I could go back even further because I was an undergraduate at Princeton as well, although I probably didn't know you back then. I was too busy enjoying the parties on Prospect Ave.
Parties in Princeton?
Yeah, believe it. All right, so it's a pleasure to be here. Thank you all for coming. I'm going to try to make the next hour and a half as tolerable as possible with a fair amount of background. So where we're headed today, the roadmap is to explain to you a bunch of the theory in this recent paper that with my colleagues, one of whom is Dirk Peschke, who I think is here. There's Dirk. That's Dirk. Yep. So that just came out in Journal of Fluid Mechanics, and then some additional theory associated with that paper. Basically our goal is to model this problem. And what is that? It looks very simple. It's a fluid with particles, but they're non-neutrally buoyant particles, so they move differently from the fluid because they want to either settle or rise due to gravity. So we're gonna try to understand this fairly simple experiment, and you're going to see that actually there's quite a lot of very interesting physics there. But along the way of trying to understand this experiment, we're also going to take a bit of a tour through some of the basic theory of hyperbolic conservation laws and how it relates to these kinds of problems in fluid dynamics. So, and some of the work that I'm going to show you includes experiments that were done at UCLA, and you guys might say, wait a minute, you're not an experimentalist, and that's absolutely correct. But these are fairly simple experiments with fairly interesting mathematics, and that was part of my goal when we set up our little fluids lab at UCLA. So this is actually, these are experiments done in, believe it or not, the applied math laboratory in the math department. That's the door sign for our little lab at UCLA. So. Okay, and I have to, the usual thing, I have to thank a bunch of sponsors, including the U.S. National Science Foundation, a grant from the UC Lab Fees Research Program. This is a joint program with the DOE labs between the University of California and the DOE labs. And also, we've had a lot of, not all of these students, but we've had a number of undergraduates working in our lab, and they are primarily supported by what are called workforce grants. These are basically training grants for younger students. So one of the reasons why I got some recent money to work on this is because a few years ago we had Deepwater Horizon, where a lot of crude oil ended up in the ocean, and then on the beaches in the US. This is a picture of crude oil on one of the beaches in Mississippi. And so what you're seeing, of course, is oil and sand on a beach, and they're trying to understand how the oil is going to flow on the beach. And so it turned out for a few years before that, we were actually doing experiments in our lab at UCLA with oil and, well, I would say a controlled version of sand, actually sand blasting beads, because you can buy them in very uniform sizes and densities. So now I want to talk to you about the mathematics associated with these kinds of flows. And to do this problem justice, I want to go all the way back to a now very classical paper by Hubbard from 1982, came out in Nature, on exactly this problem, but with a clear fluid, so no particles. So we're going to start with the problem without any particles, and we're going to understand a little bit about the mathematics associated with that. So for this slide, I'm not going to derive this equation, but this equation comes from lubrication theory, and it's a one-dimensional model for the thickness of a viscous fluid on an incline as a function of space and time. So h is the height of the fluid, x is the position in the downstream direction, alpha is the inclination angle, nu is the viscosity of the fluid, g is gravity. And the only other constant we need to know here is a, which is the entire cross-sectional area of this fluid. Okay, so So using basic lubrication theory, we can actually derive, and Huppert did this, the following partial differential equation for the film height as a function of space and time. And then he wrote down an exact solution. He said, well, actually, there's a solution to this. It looks like this. It's actually a similarity solution. It's self-similar. H has this interesting form like a square root. So if we draw a picture of what that square root looks like, right? If this is my x-axis, so it looks like this, and then the solution ends at some value xn. And he even wrote down a formula for that position xn. The formula depends explicitly on all these physical constants in the problem. And then he went and did experiments. So here are data, a bunch of data points from various experiments, and comparing them with the fit to this theory for xn. And you can see that they're really quite bang on. So he really nailed that thing. And so the first thing I want to do is I want to talk about how one comes up with a theory like this, but more from a mathematical perspective than the perspective in the Nature paper. Why? Because when we go on to studying exactly this geometry for particle-laden flow, we're going to have to couple the motion of the particles to the fluid. We're going to want to use a continuum theory like this one, but the complexity of the mathematics is going to be much more, it's going to be much harder than just this single, this turns out to be a conservation law. And we're really going to have to dig a little bit into the theory of conservation laws to be able to understand this class of problems. And so along with that, I'm going to try to describe to you, my group has been working on these particle flow problems for, gosh, I would say maybe 7 years or so, basically ever since a couple years after I got to UCLA 10 years ago. Okay, so since this is a broad audience with a lot of students, what I want to do is review a little bit the theory of conservation laws first for single conservation laws, scalar conservation laws like this one here, and then for systems of conservation laws, specifically 2 by 2, because that's the relevant case where we have a single particle species. So I'm going to do a little bit on the board, and then I'm going to go back to the science, okay? All right, so this equation here, and I'm going to try to stick with the nomenclature that we have here. So we're looking for the film thickness h, and this equation is an example of a general scalar conservation law, okay? Okay, so I'm going to assume all my constants are 1 for now. You can just absorb them, and for this audience, I don't think I need to go into detail about how you do that. But the physical constants, you can write this in dimensionless form and absorb them into the time and the length scales, so that we can write down a very simple equation like this. And for the Huppert problem, right? For the Huppert problem, f of h, we can just write as h cubed if we want to. Notice that I have the derivative. My derivative is outside the flux function. So f is called the flux function. Here, he's computed the derivative out, right? So the derivative of h cubed is h squared times hx, the x derivative. So that's why this equation looks a little bit different from what I've written here. But it's important that we think about, so for conservation laws, the theory of conservation laws, we want to write the equation in conservation form, which means it has to be written in this form, okay? And so there are a lot of things I could tell you about conservation laws, and I'm not going to give hours of lectures on conservation laws, but a couple of things that are important to know is one is characteristics. So characteristics are important because for smooth solutions, information is basically transported along characteristics. So to understand characteristics, I then have to go back and differentiate this equation. And I get ht plus f prime of h, hx equals 0. And I realize that this equation is just a material derivative of h along particle paths that move with speed that's f prime of h. Okay, so that allows us to solve this thing using what's called the method of characteristics in the case where you have smooth solutions. However, in many interesting problems, including this one right here, and you can see right here, we don't always have smooth solutions. So this is an example of a non-smooth solution that we have a jump discontinuity from the right at this position xn in the Hubbard solution. We have a jump discontinuity. So when you have jump discontinuities in conservation laws, suddenly this term, right, the x derivative of f of h, if h is jumping, then f of h is typically jumping too in space. So you can't really take a derivative of that. So how do we understand mathematically these jump discontinuities? And there's a whole theory in PDEs that deals with that. I'm not going to give a long lecture, but I'm going to describe in words what you do. So if you want to derive a rigorous theory for what are called shocks, this would be an example of a shock. What you do is you take the PDE. If you want to make it completely rigorous, you have to define what are called weak solutions, where you take a test function, you integrate the PDE, you multiply by a test function, integrate by parts, and put all the derivatives on the test function, on the smooth test function. And then you look for solutions. Then suddenly you start to be able to consider solutions with jump discontinuities. And you can ask yourself, if you have a bona fide weak solution with a jump discontinuity, what does the jump have to do? Okay? And it turns out you can derive a very simple equation called the Rankine-Hugoniot jump condition. And it literally comes from the conservation law. You can think of it as a generalization of conservation of mass if you want to. Okay? And the Rankine-Hugoniot jump condition says that if you have a jump discontinuity where we have h left here, h right here, and the jump is located at some value that moves with speed s, then the speed of that shock is given by the following formula. It's f of h left minus f of h right. So the jump in the flux divided by the jump in h left minus h right. And you can see that in the case where the solution actually is continuous, if you take the limit as h left approaches h right, this starts to look like f prime, right? If you think about calculus, if I let these two values get very close to each other, h left and h right, then the shock speed should approach f prime, which is exactly the characteristic speed. So it's consistent with the continuum form of the equation. But it generalizes to these shocks. So the first thing we would like to check, and I'm not going to do the algebra just because I don't have time, but you can take Hubbard's solution. So he has a formula, right? So he has a formula for xn, and he has a formula for h. And so you can figure out h left by plugging xn into this formula for h, and that gives you h left for that shock. And then you can also, and h right is just 0, so that's an easy one. And you can plug it in. And you can also compute the speed of that shock because we have this formula for xn, right? And I can take the time derivative of this. And if you compute that speed and you plug it in over here, you will discover that his solution does indeed satisfy the Rankine-Hugoniot jump condition, as we've written it down here. I suspect he came up with the formula in a slightly different way. And there are tricks one can use, just basic conservation of mass and so forth, to derive that. But anyway, so that's a little bit of the theory. So shocks, these are shocks. So one of the most important building blocks of understanding solutions of scalar conservation laws is understanding this basic idea of a shock and this Rankine-Hugoniot condition. Now, something interesting, so if you're really paying attention, if this were the morning and not after lunch, and everyone was wide awake, you might notice that I could take a reverse shock, right? I could take h left like this and h right like this with the same values, only flip them. I get the same shock speed if I choose my shock to look like this than if I choose it to look like this, right? And so you might ask, well, can I have, for this particular conservation law, am I allowed to have both solutions as shock solutions to this equation? And the answer is no, I'm not. And why? Because there's yet another condition I have to satisfy, and that's called the entropy condition. So let me find my eraser, and let me erase the bad one. Okay, So the good picture is relevant for this particular choice of F. But if I were modeling a very different physical example, like traffic flow, so in this case, I have at least for positive H, I have a convex flux function. So it turns out for convex fluxes, I'm allowed to have a shock if the left state is bigger than the right state. Okay, but in the case of traffic flow, you can actually use exactly this class of equations to model the density of cars in traffic. Okay, and that flux function is actually concave. And so a reasonable shock for traffic flow would have this kind of structure where the denser traffic is ahead of you and the lighter traffic is behind you. And that's exactly what you experience if you're driving in traffic on the highway, which I do all the time in Los Angeles, so I'm very familiar with this. You know, the traffic is light, and all of a sudden there's this wall of cars in front of you. That is a shock. That's a beautiful example of a shock. This case would correspond to what happens when you're stopped at a traffic light. Here's the light. Here are the cars stopped at the light. They're densely packed. The light turns green, and then you go. That shock does not propagate. Okay, you don't have all of the cars maintain their tightly packed density. In fact, they start to spread out as soon as the traffic light turns green, and that means that we need to introduce another class of solutions besides shocks as sort of a fundamental building block of solutions. And these are called the rarefaction solutions. So let me write that word down. So rarefactions are beautiful similarity solutions, exact solutions of conservation laws that have a simple self-similar form. So I have h of x and t has a very simple structure. It's going to be big H of x over t, which I can write as big H of c. And I claim that this exact solution written down by Huppert is an example of one of these. And in fact, you can see it is, because I have x to the 1/2 divided by t to the 1/2. So that's the square root of x over t, which is the square root of c in these variables. So this is an example of a rarefaction solution. And we can write down the equation that the rarefactions have to satisfy by just taking this simple ansatz and plugging it into the conservation law form, right? So if we do that, right, if I take this equation, if I take this ansatz here, this big H of c, and plug it into my conservation law, then, okay, so let's do that. So I'm going to get minus, so the time derivative of this is going to be minus, what is it? It's going to be minus x over t squared, hopefully I get this right, h prime of c, and then I'm going to need the spatial derivative, so that's going to be f of big H x equals 0, but now I have to compute this out. So this is f prime of big H. hx is going to be 1 over t h prime, and so let's put, and now I'm going to rewrite this part as minus c times 1 over t h prime, and then a plus here. So I'm doing this kind of fast, and that all equals 0. So now I'm going to multiply by t, and I'm going to pull out the factor of h prime, and I see that the rarefaction equation gives me h prime times minus c plus f prime of h equals 0. So that tells you either h prime is 0, which is boring, right? That's just a constant, but that's a relevant solution. That's important to know. Or we have that f prime of h is equal to c, or h is f prime inverse of c. And so this is the general form for the rarefaction. So we shouldn't be surprised that we see a square root here, because if our flux function is h cubed, then f prime is 1/3 h squared, and then the inverse is the square root times the constant, right? So you get h constants, right? But that's exactly where the square root comes from, because we're using a cubic flux function, and then the rarefaction has to have the square root structure to it. So that's basically, in a nutshell, what you need to know to understand the Huppert solution for the clear fluid problem. Now, of course, there's a lot more physics here that gets interesting. One of the things he talks about is the role of the contact line and the fact that you have this fingering instability, and none of that is captured by this one-dimensional model. And I am mainly going to focus on the one-dimensional models today. But I just wanted to mention that because there are a lot of very interesting problems out there. Okay, so now, what is the problem that we want to study? It's basically Hubbard with particles, in this case, beach sand. Okay, now this is, this is like all of the interesting stuff exposed. So I'm going to tell you what I know and what I don't know. So first of all, we had fun. We actually went to Santa Monica Beach. I think the students went there. They went to Santa Monica Beach, which is very close to UCLA, got some sand from the beach. And these are two experiments with essentially the same parameters, the same volume of sand, the same volume of fluid, the same way of mixing them, with one very important difference in the preparation that leads to completely different behavior. And I'm really only going to talk about this case, but in case you're curious, any guesses as to what's different here? Gives you an idea of how sensitive this problem can be to fairly small changes to the capillary physics. So the difference here is when you go pick sand off the beach, and this is certainly true here in England, and it's even true in sunny, dry California, when you take sand off the beach, it's not completely dry. So this was sand straight off the beach that seemed dry. This was sand that we dried more, so by sticking it in our microwave oven in the lab. So this is extra dry sand, and this is sand that we thought was dry, but really wasn't dry. So just a small, maybe 1% water can cause rather dramatic changes in the behavior. I don't know how to model this one. This one I think we've got a good handle on, and that's what I'm going to talk about. So, and you can see that this problem here is begging for us to introduce some kind of continuum theory that allows us to understand, what is the position of this leading edge of the sand compared to this front of fluid. So we've got a couple of different structures. It's more complicated than the original Hubbard problem, and quite more complicated. Now I'm going to tell you kind of what we did. Oh, here's another. So this is all dry sand. And what you can see is that there's different phenomenon that we want to try to understand. So in this example, notice that here there's sand all the way to the leading edge of the front. In fact, quite a lot of sand. The sand seems to be collecting there. Here we actually have clear fluid leading the flow. So there are very different types of dynamics we can see, all depending on the inclination angle and initial concentration of the particles in the flow. So I think we're at a point now where we have a pretty good handle on all of this stuff, but it's taken us quite a while. All right.
Can you tell us why PDMS?
So why are we using PDMS? It does not absorb water, moisture from the air. And so it just sits there in the lab and doesn't change. You can buy it in a million different viscosities, which we did, just to see if that changed anything. It changes the time scale of the experiment, not much else. It also wets everything. So if you're worried about contact line effects, PDMS is a good reproducible chemical. It's also pretty harmless. We don't have to worry about complicated cleaning procedures, although we did get in trouble with neighbors near our lab because apparently very small traces of PDMS on a waxed floor make your shoes squeak if you're wearing these kinds of shoes. So people were not impressed with that. So, but we found a solution for that too. So, yes. Hubbard was just clear fluid, no particles at all.
And the connection,
very simple.
What you were looking at here is
I'm going to try to explain how we try to model the particles now. We're going to try to redo Hubbard with particles.
okay.
And it took us a number of years to get what I think is a good model. So I want to go through some of the modeling that we did. And in order to do that, I need to introduce some ideas from systems of conservation laws. But I need to motivate why systems first. So let me go through some modeling. All right, so the movie suggests that we ought to be able to, at least to leading order, still use continuum theory, even though we have discrete particles, because we have a large volume of them. they're fairly small compared to the other length scales in the experiment. We were using, I don't know, 300 micron particle sandblasting beads, very similar to the diameter of sand on the beach. So we thought to leading order we could try this. So without going into a lot of heavy detail, I will just say the parameters we need for the model. We need to know the local particle concentration. These are just the usual parameters from lubrication theory. Let's see, the volume average flux. So we do have to keep track of fluid stuff and particle stuff. So we've got flux of particles, flux of fluid, flux of both things. So the first model that we wrote down was a joint paper with Pekko Hasoy's group at MIT. And I need to give them a lot of credit because the problem really originated with the group at MIT. I was visiting in the fall of 2003, and they said, hey, we've got interesting stuff with shocks. Why don't you come and work on the shocks? So that's what I did. And then got really into it and decided to try to do a bunch of the work at UCLA. All right, so now we have to put in new physics. So the very first physics we put in was settling of particles. So these particles, the ones I showed you, sand, glass, the sandblasting beads, they tend to be about 2.5 times more dense than the background fluid. So they're sinking. And so we have to think about what happens when you have a particle sinking in a fluid, in a viscous fluid. So the first thing you want to think about is the Stokes settling law. For those of you familiar with this problem in fluid dynamics, there's a classical formula which is this formula times gravity. Forget these two terms for the moment. If I have a single particle of a fixed diameter, and that's this parameter here, and I just let it settle in a viscous fluid, it reaches an equilibrium speed called the Stokes settling speed, which you can read off from this formula. And now there's other terms here, and those terms represent what happens when I have additional boundaries in my fluid. And most importantly, if I have a lot of other particles, they will hinder the settling of each other, right? So that's because the fluid is incompressible. So when I have a particle settling in the fluid, it displaces the fluid around it. And that will interact with other particles, and they will interact with each other. So if you have a lot of particles together, they cannot settle with the Stokes settling speed. They're hindered in their settling. They settle more slowly. And to date, we do not have a first principles formula for the hindrance function, which is this here. But we're going to assume it's just a function of the local concentration phi. This is a wall effect, which turned out to be very important for the first model, but not so important for the later model that has more physics in it. So I'm not going to talk too much about the wall effect, because it's really only important very close to the wall where h equals 0, the substrate. So there are a bunch of different models out there. So this is one model for settling, kind of in an intermediate regime called the Richardson-Zaki model. So it scales like 1 minus phi to some power. We also need to know how the local viscosity of the mixture changes with the local concentration of particles. And here phi max is the maximum packing fraction. It is not 1. Okay, if you just think about how many spheres you can put inside some volume. In the actual experiment, we were able to measure at about 0.59. We don't have completely uniform particle size. There is a small variation in particle sizes, and it's an experiment, so you have to measure that. Okay, so with that physics, and only that physics, so hindered settling and nothing else, we were able to derive, and this is our lubrication model. It looks kind of ugly. But yeah, this is what you get. This also has surface tension. So you can see this is a surface tension term here. So that's all the physics: surface tension, hindered settling, the gravitational flow. This was modeled on a earlier paper from my group with Michael Brenner from 1997, basically the Huppert problem rescaled. So now, if you want to turn it into a conservation law, you drop all the higher order terms, which is easy to do in PowerPoint because you just put big red X's over them. Okay. So now I have two equations, right? One for this thing and one for this thing, and both of the equations have terms that only depend on the first derivative because I've dropped all the higher derivatives in x. So that's what it is. And then if you kind of stare at them, you discover that what you have, if I set u to be this quantity and v to be this quantity, I now have something that looks like a 2-by-2 system of conservation laws. So this is a generalization of this single conservation law. And so to understand the solutions, to understand the theory based on this physics that I'm showing you today, right now, I need to know something about what happens if I want to solve this 2-by-2 system. So now I have two variables u and v instead of the single variable h, and I have not one flux function, but two, one that corresponds to this equation and one that corresponds to this equation. Yeah, Uwe.
Weren't fire the volume concentrations they adapt to one?
Yeah, so we've got, so the density is going to depend on the local volume fractions, volume fraction of particles.
If those together you get h.
Uh,
And there's enough h.
You can get an equation for h. I don't, off the top of my head, I can't tell you if that's the right way to do it. But yes, you can get an equation for h, as you would expect. So there's a number of different ways you can set this up. So that's a good point. There are a number of different ways you can set up the conservation laws.
The stresses come from Richardson-Zaki.
Yeah, and so the stress is right, exactly. So what's happening is that the particles are not flowing uniformly with the fluid because they have, so we're thinking about the settling as not just in the direction normal to the substrate because we're on an angle. A lot of it's actually going to be, the settling is going to be in the direction of the flow. Okay, but using Richardson-Zaki as a preferential settling. Okay, so you can put all of this together. So the first question is what happens if you use just this physics? So let me kind of, since we have a lot of students and not everyone knows about conservation laws at this level, I'm guessing. Maybe you do, and this is, you can relax, but here we go. Okay, so why don't we just commit this to memory, and I'm going to erase this. But I'm going to rewrite it for the system case. I'm going to rewrite the Rankine-Hugoniot condition for the systems. And we're going to see something really complex happens, but very interesting. Okay, so what happens is, so now let me just write those equations. ut plus f of uvx equals 0, and vt plus g of uv x equals 0. So now what I want to do is this idea that I used to derive the jump condition for a shock, it generalizes completely to the 2-by-2 system case. So the Rankine-Hugoniot jump condition, I can literally just write it down by looking at this. So I'm going to do that. You'll humor me, allow me to do that. So, okay, so I'm going to assume that I have, again, I'm going to assume that I have u left, but now I have to have a left state for u and a left state for v. So I have u left and v left, and I have u right and v right, and I have a jump discontinuity from these states propagating with speed s. So let's just assume we have that, and let's see what s has to satisfy. So now I'm going to have two conditions for s, one from each of these two equations. So the first equation is going to give me that the shock speed is equal to, so it's the jump in f of u left, v left, minus f of u right, v right, divided by the jump in u left minus u right. But that same shock speed has to also satisfy this equation in weak form. So that gives me the jump in the g flux divided by the jump in v. Okay, so now you see where the problem is, because if you just give me your favorite fluxes f and g and your favorite left and right states, I may not get the same shock speed with these two formulas. There's no reason why I should, right? It's overdetermined. I cannot solve this in general. So now you may wonder, well, how the heck do you get shocks from a 2-by-2 conservation law? And the answer is you can, but you're going to have some restrictions on what the left and the right states are allowed to be. Okay? So that's the trick. And so So there are different games you can play with these conservation law problems. One game you can play is called the Riemann problem. It's a famous problem in PDEs where you specify the left, and we're going to want to play that game. We're going to specify this state, we're going to specify this state, and then we're going to try to find a weak solution of the PDE that satisfies everything we want to satisfy. And we're going to discover that in general it's not going to be a single shock, but it might, and where's my eraser? Oh, it's over there. It's a little complicated with two boards on different sides of the room, but it's good exercise, right? So we might not want a solution that looks like that, but we might allow ourselves to have a solution that has an intermediate state, which we have to figure out, and two shocks, S1 and S2. So I'm not going to go through, because I don't have a lot of board space, so let me just say, if you write down the Rankine-Hugoniot condition for this one and for this one, altogether you're going to get 4 equations, and guess what? You have 4 unknowns. You have 2 unknown shock speeds, and you have the 2 unknown intermediate states. So if all is well in the world, you might be able to solve that. Now, I got a little bit fast, and I left out the entropy condition for the scalar law case, and that's important. So let me write that down. I'm going to erase this here. And I'm going to remind everybody that for the scalar law problem, right, this was my scalar law, right? So for the scalar law problem, to have a bona fide solution that's a shock, I have to satisfy what's called the entropy condition. Well, there's a more general condition, but let's consider just the convex flux case. So the entropy condition, I'm going to draw a picture. I like the characteristic diagram picture. So if this is X and this is T, the entropy condition is equivalent to saying the characteristics enter the shock on both sides. And it has a formula which says that the shock speed, so that's the speed of this thing, has to be bigger than the characteristic speed to the right, that's f prime of h right, and it has to be less than the characteristic speed on the left. Okay, so this condition tells us, remember I had those examples of a good shock and a bad shock. The good shock satisfies this, the bad shock does not. And so in this problem here, having 4 equations and 4 unknowns and finding a solution does not guarantee that that solution is going to be what you find when you simulate the PDE numerically. Those shocks also have to satisfy a generalization of this entropy condition. And so I could write it down, but I think I'm not going to because I'm going to confuse you with lots of nomenclature if I do that. I think I'm just going to show you some pictures. All right, so here are some pictures. So if we take this model that I just showed you and we simulate it numerically, the first thing we did was we wanted to see if we were, remember how I put those red X's? So we had a really good student at MIT who could simulate anything. So he actually simulated that full problem with all those crazy terms. And then he threw out the ones that had those X's and compared the two. And this is the height of the film. This is a Riemann initial condition, by the way. And this is the height of the film, the concentration, and the reduced model is in the dark color and the full model is in the light color. And you can see the throwing out surface tension of those extra terms still gives us a leading order approximation, which is pretty much bang on. So we're good working with the conservation law. That was the first thing we did, because otherwise why bother with all this analysis, right? Well, okay, so there's numerical diffusion. But believe it or not, this is a double shock forming here. This is one of those things over there, and this is from a paper we published in PRL in 2005, and we worked out the theory for this. We checked it against the Rankine-Hugoniot conditions, and there they are, just what I wrote down. Those are the four equations and 4 unknowns. And so you can actually predict the intermediate states just from solving this algebraic problem, and then you can go back and see if it agrees with the numerics of the PDE, and in this case it did. But one of the things that you see, so now this is where the PDE theory for conservation laws gets very interesting, because something happens here that doesn't happen in scalar laws. For scalar laws, you always have a nice solution that either has jumps, shocks, or rarefactions, and there's really nothing else. I mean, if you start with a Riemann initial condition, the only thing you're going to get is something that pieces together shocks and rarefactions. That's all you're going to get. But something really interesting happens here, because there's a parameter in our model we can vary. We call it the precursor film thickness. For those of you in thin films, you know exactly what I'm talking about. For the rest of you, just don't worry too much about it. It's just the downstream thickness in the model. As we make this get smaller, we discover that those shock speeds converge. That's not good, because suddenly this solution goes away. And we no longer have that solution, and we no longer can find a bounded solution of the Riemann problem. And so something very interesting happens. So this is another kind of diagram that you can do. This is another game you can do as part of this solution. This is called the Hugonio locus. And so the game you play is, this is another game of this type here. So what you do is you take your left state and you take your right. So here's a right state. And so this is phi and h, so it's a plane, right? So it's a plane, because it's a 2x2 system. So this is my right state, so it's a point in my phi h plane, and then the left state is this square, and that's a point in the phi h plane too. And what are all these lines? These lines are loci of either left or right connections that allow us to solve the Rankine-Hugonio jump condition, either for the one shock or the two shocks. So it gets to, there's some bookkeeping you have to do, because there are one shocks, what we call one shocks and two shocks, and they satisfy different entropy conditions depending on which kinds of shocks they are. But to give you a flavor, overall flavor, this is the game that you play, and then you look for intersections from the right state to the left state, and those intersections, if all is well in the world, will correspond to your intermediate state. So this point here, let's see, yeah. So this point here is the intermediate state corresponding to this right state and this left state. And you see what happens when we take a very small right state, that's the precursor thickness getting small, suddenly the Hugonio locus for this state is this little loop over here that never makes its way over to the locus from this solution here. This is work by my former PhD student, Ben Cook. So that is a topological picture of what happens in the 2x2 conservation laws, that we never see that phenomenon at all in the example of just the single conservation laws. And all we did was add particles. So what happens if you actually solve the PDE numerically in this bad situation, you discover that you get mass concentration. You get accumulation of mass at the leading edge of the front, and you develop something that we call in PDEs a singular shock. And so one has to then develop a theory for singular shocks. But we discovered that a very small change, not a small, but a relatively important change to the physics in the model changed that behavior completely. And so what did we do? Well, what we did was we took a look at this empirical settling function, right? So if we go back past all that stuff and we go to this, so Richardson-Zaki does well in an intermediate range of phi, but it does not do well near the maximum packing fraction, and that's exactly where you end up in the singular shock. You're very close to the, or if not at the maximum packing fraction. So suddenly we're using a physical model that's really not good. So what we did was Ben went back and redid these calculations with a different model. This is the Buskell model, which makes a lot more sense physically at the high concentration limits. And suddenly, this issue with the Hugonio locus goes away completely, and we're able to connect our left states and the right states for arbitrarily small precursor thickness. You can see the topology of these connections has changed completely with this different model. So we were very happy about that. And then I won't get into a lot of this because, let's see, I have until what, like 4:30, right?
A little bit.
Yeah, so I'm just going to say that you can take this nice model and you can actually take it, you can add surface tension, you can put it in 2D. I had a PhD student, Matthew Mata, who did that. He did ADI simulations on parallel machines, got beautiful pictures of fingers with particles. Here are the particles. So all of this is great, and it scales nicely in parallel, and it agrees with experiments, and it's all beautiful. But then what we discover is that this model that we're using only tells us something about one sort of regime for the experiments. So that's, let's see, I need to figure out how I get there we go. So this is what we call the ridged regime, where you have particles collecting near the front. Right there it is. But it does not explain what happens here, right? So here's another regime where you have particles settling to the substrate and you have clear fluid. And so our model that model completely neglects this effect. And so my student Ben Cook was really concerned about this. You know, he had done all this lovely work with the shocks for the first model and said, yeah, but we're completely missing this physics. So he went back and came up with a very nice idea to understand this transition as we change inclination angle and particle concentration. So here are 3 pictures from our lab, just to show you what I'm talking about. Small inclination angle and small concentration, and you can see the sand really settles to the substrate and there's clear fluid flowing over it. This is the large case. Here we've got particles collecting near the front of the flow, and here is sort of an intermediate regime where everything kind of stays well mixed. And so you can actually so we've had students generate phase diagrams. Let me see if I can show you one. Here it is. So we had a bunch of undergraduates do just a whole series. So every dot on this is one experiment. So this is a huge number of experiments that they're doing. And they're comparing inclination angle to the initial particle concentration of the mixture. So they start with a very well-mixed mixture. They pour it at the top of the slope. It goes down, and then it's going to go into one of these 3 regimes, and you color it either white, dark, or this sort of intermediate gray, depending on which regime. And so the beauty of these plots is that there is a solid line in addition to the experimental data, and that solid line is a line corresponding to this theory, and it basically agrees extremely well with the theory. And this was due to my student Ben Cook. And these experiments were published a couple years ago in Physica D. They were overseen by Nebo Murisic, who was a postdoc at UCLA. So now let me tell you a little bit about that theory, because I think it's kind of pretty. So the theory brings in another piece of physics that I haven't told you about yet, but something that's incredibly important when you have particles trapped in a thin film. So the thin film geometry is really critical here. So what's special about a thin film? And you might think it's pretty boring. I mean, it's just viscous liquid on an incline. Well, it has a free surface. So when you have the free surface, that free surface can be moving rather fast, but the fluid has to satisfy a no-slip condition on the solid substrate, which means that you have a rather high rate of shear within a very thin film. So you've got shear. So it turns out when you put particles in a shear, they move in unusual ways, especially if it's not just one particle, but a lot of particles which are, you know, kind of bouncing around with respect to each other. You have something called shear-induced migration. So the particles move. So in fact, what you get is a situation where, and you can do this back of the envelope calculation. If there's no migration, then basically, because of the fact that this is a fairly thin layer, at almost every inclination angle, we should see the particles just settle. We should normally see that if we had no migration. But because of the shear-induced migration, these particles get re-entrained in the flow. They get pulled back up into the flow, and that's why we see this very rich structure, this very rich phase diagram through a range of inclination angles. Okay, so the model that we used, we didn't invent. So people have been studying shear-induced migration of particle fluid systems for a while, just not in this geometry. So we had the benefit of a lot of papers that have already been out there in things like Couette geometry, no free surface, basically in geometries without a free surface, where they've been able to measure empirically this and come up with models for this. So I won't go into too much detail on the model, but I'll just say that we basically took this off the shelf from the existing literature. And so basically our goal was to derive, so since this is lubrication theory, we actually wanted to come up with a steady state profile for the particle concentration in the layer, assuming that we're solving the Stokes equations with shear-induced migration. So what you get is a coupled set of ODEs as a function of z, the position through the layer. See, there's your z, for the shear stress and the particle concentration coupled together. So these are the coupled ODEs. You have boundary conditions that are just your natural boundary conditions associated with the fluid dynamics. You know, 0 shear stress on the top surface. The particles don't go through the wall, basic things like that. And then you can solve these ODEs depending on, so we have two parameters for the solution of the ODEs. Let's just assume that the thickness of the film is fixed, and we're going to play with the average particle concentration through the layer, and we're going to play with the inclination angle, just those two. So then I can solve those ODEs, and I get the following solutions that depend on those conditions, and there's a beautiful bifurcation. Okay, so what am I looking at? So this is z. This is actually, so let me draw z on the Huppert diagram so you can see what z is. Z is this direction. So z gets, when you do lubrication theory, z is averaged. So this is actually pre-lubrication theory. Okay, so we're trying to compute the local equilibrium particle distribution in the z direction. And so now this is turned on its side, because now z is in this direction. This is sort of a bad picture, but it's prettier to look at this way. So z is on its side, so now this is z. So we can see that for small values of the average particle concentration, they are indeed kind of stuck to the bottom, right? So here are just different, we're just seeing a lot of different solutions all on top of each other. So they're stuck to the bottom, and then there's clear fluid, but then there's a critical value of the average particle concentration where they are completely uniformly distributed through the layer. Okay, and that's this value here. And then we see for large values of the total amount of particles, you actually have more particles on the top, which is very interesting because that explains why you would see this phenomenon. If you have more particles that have risen to the top, and I'm going to break this thing, if you have more particles on the top, then, I don't have a pointer anymore, but that's okay. Here, you can fix it while I talk. Okay, so you have more particles on the top. What happens is they're going to flow faster, and they're going to end up at the front of the flow, as we see in this picture right here, okay? Whereas if the particles are stuck on the bottom, the clear fluid, which moves faster because it's on top, is going to flow ahead. Thank you, Giannis. And you get this configuration here. So I like this because we have a direct connection between what seems to be very simple equilibrium theory and our dynamic experiment. But in this case, we're just taking the dynamic experiment and binning it. So each experiment gets a bin, right? It's either a circle, a triangle, or a diamond, depending on whether it looks. So it's a very simple experiment. You can undergraduates do this because all they have to do is run the experiment and say it looks like this, or it looks like this, right? It's a very simple experiment. But you have to do it many, many times. You need a lot of data. And so it turns out that equilibrium theory, which corresponds to this line right here, has a formula, and this is it. And that's these solid lines that we're looking at. And that's supposed to differentiate between the settled regime and the ridged regime. And then, of course, the intermediate regime should be a regime where it hasn't really equilibrated to either case. And so we would expect, when we have very small beads, the small beads are much closer to the colloidal situation where they stay in suspension because they're small. The time scale of settling is very long for the small beads. You would expect a rather large intermediate regime. But for large beads, they ought to settle very quickly, and indeed, we don't even have an intermediate regime in the case of the large beads. So we were very, very happy with the experimental results in this paper. So we decided, well, maybe, since we feel like we had really nailed the equilibrium theory, we could take this equilibrium theory for the structure of the fluid through this layer and now do full lubrication theory for the dynamic problem, just like Huppert did for the clear fluid. And so this is the paper that we recently published in JFM, and it involved rederiving the 2x2 system of conservation laws. Sorry about the resolution here. So we rederive a 2x2 system of conservation laws with this additional physics, and the lubrication theory involves also this averaging in the z direction of the particles. But we have to keep track of, before the average, where the particles live in the layer, because that's going to determine the fluxes of particles that we need for the new model. So you can put all of this together, and again, details that I don't have time to go into, but other than to say these are the ideas. And what we can do is basically try to redo Huppert in the case where we now have a separation of particles and fluids. So this is the analog of the Huppert experiment, but with two fronts. Instead of a single front, instead of a clear fluid with one front, we now have a particle front and a fluid front that are separating from each other. So there are two fronts that we're trying to keep track of. Okay, just like in the Huppert paper, it's a constant volume experiment. So we're not actually solving a Riemann problem. We're solving a bit more complicated problem. We're actually solving a constant volume experiment. And so what we can do is basically take the solution from the experiment. We can plot the data from the experiments, and because it's actually two fronts, you have to plot both of those fronts. So there they are. These are different inclination angles, and what you're seeing here, the lines correspond to the solution of the PDE with the same parameters as in the experiment. So we were quite happy with that because this is just a one-dimensional conservation law model, a very, very simple model. But if Huppert could get bang on in his experiment, maybe we could get the same thing. So that was our goal.
Did you come up with an F, or it's clear?
The F comes from, so we have to go, that's another talk in and of itself. But the F, so it's an F and a G, right, because it's a 2x2 system. And so in order to compute the fluxes, we have to look locally, before you go into the depth average problem, you have to consider the fact that your particles are stratified in the z direction. And that stratification tells you what the flux is, the bulk flux is going to be in X. And so that's what we do, is we use that as our ansatz. So, so Dirk and some of the other guys who really worked hard on this paper went through a lot of work to actually do the formal asymptotics for this problem. And that's why it's another, that would be a lecture unto itself. So let me just say that has been done, and it's been checked by my new postdocs too. They agree. And of course the best check is this, right? So, assuming that you believe we did the experiment correctly. And there are essentially no free parameters. There's a slight parameter that you have to pick because you don't actually, you start with a beaker of junk and you don't get all of it going down the slope because some of it's left in the container. So we had to go back and measure how much was left and subtract that volume. That's one thing. And the other thing is that there's a transient time period where the well-mixed particles haven't really separated yet. And so that we also have to estimate when that is, but you can sort of see it in the data. So we pick that from the data, but those are the only two things we have to pick. Everything else comes straight up, everything else is in the physics. There's nothing else free. Okay, so just like in Ben Cook's earlier calculations for the earlier model, we actually, for this model, we can't, so this is a beautiful discussion of what happens when you have this settled regime, but what about the ridged regime? And in fact, something very interesting happens. So with this model, we actually do also get singular shock. So if we push the particle concentration and the inclination angle to a higher level, we do not get the separation, and nor do we see it in the experiment. Rather, we get singular shocks, and with a postdoc of mine, Li Wang, we've come up with a theory. So this Rankine-Hugoniot theory for the regular shocks is very beautiful and classical. It's a much harder problem to try to get a full theory in the case where you have mass accumulation for the singular shock, because you have to have some additional constitutive law, or you have to use some kind of higher order model with asymptotics to be able to get that. So let me just say that we have a theory for that, and it's actually, the theory to derive it is actually not as hard as one would think. If one makes the following very simple ansatz, you have to assume something. So what we assume is that when you form a singular shock, that the volume fraction in the shock is at the maximum packing fraction. Okay, that it can't go above that. So there's no singularity in the particle volume concentration. There is a singularity in the mass. We just make that ansatz. If you do that, you actually can derive a formula for the shock speed in terms of the left and the right states and the fluxes and the maximum packing fraction. And it's bang on with the PDE simulation. You can also derive a formula for the rate of mass accumulation. And so one question, we have open problem. So we have a paper on this that's under review. It's a math paper. So an obvious question for us is whether this has anything to do with the actual experiment when we have a particle-rich ridge. Is the particle-rich ridge actually a singular shock, or is it something else? And so that's an open problem that I would like somebody to work on, maybe somebody in my group, maybe somebody else. So that's a cool problem. So I have about 20 minutes, and I thought I would end my talk with a little, I have a couple of things I could talk about, but I was thinking I might tell you about the spiral separator problem, since I have more physicsy people here as well as, so you've heard a lot about conservation laws today, right? And a lot of math related to conservation laws. Mainly about the shocks. There also are rarefactions in this problem. In fact, we saw some, but I didn't have time to look at those too much. But I think what I want to do is mention how this connects to spiral separators, which means I'm going to have to pull up Sung-Yun's. So these are slides that were given to me by Sung-Yun Lee, who has just finished a postdoc in our group. She's going to Texas A&M, starting this fall as tenure track. And also, this is joint work with Yvonne Stokes from Adelaide. And Yvonne was the one who actually suggested this problem. I met her a couple years ago at the ANZM meeting in Australia and had lunch with her. And she was working on the spiral separator problem. So let me tell you what that is. This is a badly resolved picture of one. But basically, these are devices used in the mining industry. They are very simple in terms of the mechanics. It's basically a big helical trough. And you need a slurry pump to pump the slurry in the top. But once you do that, there's nothing else to do. You just let gravity pull it down. And what comes out the bottom, if it works correctly, is the particles separated in little streams. So I think I have another picture. Let me see if I scroll forward. There we go. So this is from a website of a company, a Chinese company that makes separators. It's a little hard to see up close, but this is just water and sand. And so they put it in this separator, and then when it comes out the bottom, the sand is all on the inside of the spiral. And there's clear water over here. That's a simple example. What you really want to use these for is you want to put in mixtures with two different types of particles, right? Coal and maybe rocks, which can have very different densities. And you'd like to be able to have this thing separate them, and we'd like to come up with a theory. So we decided to start with the problem that we thought we could solve. So we didn't actually solve the general separator problem. I'm going to skip some of the background here and just go to what we did. So what we did was the low Reynolds number separator problem. We decided that we would look at the problem with the kind of geometry you see in real separators, but instead of thinking about a water-based slurry, we want to think about a slurry that looks like the stuff we work with in our lab. So viscous fluid. Since we understand a lot of the physics now for the viscous fluid case, we thought we'd work through that in the spiral geometry. So it's pretty cute what happens. So this is the theory. So we have a couple of parameters here. There's curvature parameter, which might not be small. There's a torsion parameter, which hopefully is small, but actually I don't think it actually needs to be that small either. But the cases that we look at correspond very much to the kinds of devices you see in industry. So in a typical industrial device, the diameter here is typically rather large compared to the distance between successive turns. So it's a fairly modest slope. So the models that we're looking, so we now have a model that would make sense. And then of course you have a free surface, but you also have the twist. So you have to figure out what happens with the twist. So all of these are equations we've already looked at, Stokes equations with transport of particles. And again, we're looking at the shear-induced migration model because we believe that's important for these kinds of geometries where you have a free surface. So that's important for the flux of particles. And then the usual boundary conditions. So this is steady-state Stokes. These are the usual boundary conditions that we have at the surfaces, and then the assumptions. So the curvature need not be very small. The torsion in this, in at least the first paper we're working on is small. Now you do have to pay attention to the particle size with respect to the film layer. So we have some constraints here as well. So here's the punchline. The punchline is so we decided to start with the easiest problem we could think of, which was to write down the steady state Stokes equations and see if we could solve them or see if we could understand what's going on. So you do this. So this is continuity. You have momentum in the x direction, the z direction, and the y direction. And yeah, and you have a Reynolds number and a Froude number. You have a shear stress. So sigma is our shear stress as before. And what's new here from the previous, just the planar geometry is this, mainly it's the centripetal component coming from the helical twist. But it turns out to make all the difference in this problem. And basically the issue is that this causes what the model is going to tell us is that there's going to be a leading order downstream flow, which we've already solved. That's basically the model that I just showed you for the planar geometry. But now we're going to have a secondary flow, which comes from this twisting component of the helix. Okay, and then the downstream flow is going to be a balance between shear-induced migration and particle settling, just like we had in the planar geometry. Okay, so just to remind everybody, she has a lovely movie here of, these are 3 different experiments in the planar geometry, and these are the different regimes that we see, and this is where the clear fluid comes out ahead, and this is where the ridged regime comes out ahead, and they're just colored. So one of the things we do in our lab is we dye the beads so you can have different colored slurries. We just use food coloring and color them and then bake them in the microwave. Okay, so, yep. All right, so now so we're looking for a steady state. And so this is where the downstream equilibrium theory is really important. Just to remind you all, we had this bifurcation for the equations of the shear stress where so we're looking for a steady state model, and it turns out the only thing that's going to be stable, a stationary model, is locally if we actually are operating right at the critical particle concentration for this flux, this shear-induced migration model. So that would be this value here. Okay, and so we're basically trying to couple this now with the secondary flow. What the secondary flow is, it causes, so the helix is going like this, right? And so the secondary flow causes fluid to be pulled in along the bottom and to flow out along the top. And these are actual solutions of the lubrication model with this additional component in it. And okay, there we go. Great. Okay, so the steady state solution has to be constant in z at each y, which means that it turns out we actually want exactly this critical phi c. Okay, so basically what you get, in a nutshell, what we end up with is a rather complex solution. So this is a cross section of a turn of the spiral. Okay, so this is the z direction. The flow direction is this way. So we're gonna watch this progress in the flow. And so it turns out that the only stable steady state we can have is to have the critical packing fraction on this side and no particles here. Basically, this is what you see, just like in that experiment I showed you with the beach sand in the spiral. So here's what's happening. So the main flow is actually in the downstream direction. So all of this stuff is trying to flow downstream. But there's also the secondary flow, okay? So the secondary flow is going to pull particles on the top into this regime without particles, and it's going to pull clear fluid into this regime here. But remember that the downstream flow is dominant, and it also is going to equilibrate very quickly according to the asymptotic theory, which means that these particles are going to settle very quickly because there's only a few of them. So they actually go to the settled state, and then the clear fluid will rise to the top. And then what happens is it corrects itself and goes back to the situation again. So it's a self-correcting jump discontinuity in the particle concentration. And so I have sort of a heuristic picture. So not all of this is rigorous mathematics. Some of it's very heuristic, but it makes sense at least. Okay, So that's the idea. So basically, if you give me the total volume fraction of particles coming in at the top of the slurry, I can make this calculation and figure out exactly where this line has to be and tell you, tell you what they're going to look like when they come out the bottom. That's the idea, assuming that the steady state model is correct. So that's a big assumption too. Right. So anyway, so we have an exact solution that looks like that. And so this is just another picture. These are the streamlines. So the streamlines are pretty boring. This is the particle-rich section of the flow, and then this is the clear fluid section. And you notice that this model is rather special because it's just for one particle species. I don't have two particles in this. The real mining problems actually would have at least two species of particles. Let's see what happened. That beautiful picture went away. There it is. Yeah, so this is just another picture of this reentrainment. So basically, if you have the particles on the inside of the turn at the right concentration, then the secondary flow, which is going to try to destabilize this, actually gets corrected on a faster time scale than the flow is. And this turns out to be, at least if you look at the time scales, hopefully a stable configuration. So where we'd like to go with this is we'd like to actually understand how you can get separation not just of a single species in a clear fluid, but of two different density species and a clear fluid. So what we're working on right now is not this problem, but the inclined plane problem with two species. So we've done some experiments with that, and we're working on the fluid dynamic model for that. And so I think since you've seen all that. So I think since I've talked quite a lot today, and it's late, that I might just stop there. And thank you guys for coming.
Question? Please.
Uwe, yes.
When you have this transition between the two vertical concentration profiles, what in the second case, what does pull the concentration up towards the free surface? I mean, it's surface.
It's the shear-induced migration. So you have to look at all the terms in the shear-induced migration. I can't say any more than it's the complex physics of shear-induced migration that pulls them up.
Do we believe the...
But it's completely consistent with the experiment, because if you didn't have more particles on the top, you wouldn't see this collection of particles at the leading edge of the fluid either. So what I'm doing is comparing local equilibrium theory with the global behavior, but it's completely consistent with that. What we haven't done, which is high on our list to do, is to compare the dynamic models, right, with the experiment. So we haven't done that. That's on our to-do list for this problem.
Does this mean that the Richardson transactions or the other expression you had, they are assumed to be valid all the way from phi 0?
Yeah, that's a good point. That's a good point too. When you get close to maximum packing fraction, we don't expect Richardson-Zaki to be correct. Not quantitatively.
Is it also supposed to be? This is I should know as a chemical engineer.
Yeah.
Is it supposed to be good close to small feet, like even if
it's actually intermediate, where I think it's best. I mean, I'm not the world's expert either.
I think it's more for fluidized beds, not so much for few.
Yeah, exactly, but not at the highest concentrations either. So some intermediate concentrations, maybe 30-40% volume fraction, it might be fine. But 55% volume fraction, probably not, and 2% volume fraction, probably. 2% is not interesting to us anyway, right? So we're interested in something in the intermediate.
Does the full PDs, they have self-similar solutions or not really?
Yes. Okay. Good question. So the full PDEs, meaning the 2x2 system of conservation laws. So 2x2 systems of conservation laws do have similarity solutions. There are rarefaction solutions.
The ones with the terms that you asked, if the full equation.
No.
No. Okay.
No, and they shouldn't. They shouldn't, because you have different length scales on which those terms interact. Okay. And so no, and we know that. That's I mean, if you want to make the problem really simple and start with Riemann initial data and just a single shock with surface tension, then you can look for traveling wave solutions. And there's a lot of people who've played that game for just the clear fluid problem with surface tension. So that would be an example of a similarity solution. But in general, no.
I think an interesting extension of this, Andrea, might be to start taking, let's say, the physical characteristics of the particles into account. For example, let's say I'm trying to imagine a case where particles, let's say, are non-wetting in the fluid or partially wetting.
Right.
They would like to try to move into the interface, where there will be some kind of absorption-desorption process there, and then they will try to position themselves in a way that they have a certain contact angle between the liquid and themselves. You see what I mean?
That's not a small modification.
That's
No,
it, though. That's
I'm
a,
just saying, I'm
yeah.
trying to think ahead. That's all. If I wanted to, let's say, look at a situation where...
So, Seraphim, you've brought up a really good question, and let me tell you where I think that question fits in the context of what we're interested in. So what I haven't showed you at all, I've completely bypassed this issue, it's an important one, is putting surface tension in the model.
Oh, nice. That would be...
On the free surface. I mean, if we want to do fingers, you can see the fingers in the experiment, especially in the ridged regime. One of the things we've noticed is that when you have the ridged regime, the number of fingers goes way down. There's a suppression of fingering.
Yes.
And you cannot predict that from basic clear fluid surface tension theory, because the mixture is acting like a highly viscous fluid. You would think that to leading order it would be like the same stuff, only with a higher like a clear fluid with higher viscosity. That should have the same number of fingers, right, as you know, as a low viscosity fluid, and it doesn't.
Oh,
and the question is why, and I don't know the answer to that.
Why?
Yeah, and that's a wide open question. It's a beautiful question, and to do it correctly, we need to get the surface tension modeled correctly with particles.
Because these are not surfactants, they are particles.
They're particles.
That's right. So one has to think then about the thermodynamics of particles.
Absolutely.
Yes, nice. No,
You have ideas? Be happy to talk to you about
We
them.
can talk, yeah.
Okay, great.
Thank you.
This is the practical thing about the coloured particles that you had before. I wonder if you've tried having basically the same thing but having different colours, so you arrange them in stripes to begin with, for instance.
We do.
And
We
you sort of
do.
mix that kind of
I don't have it in my PowerPoint, but we do for the specific problem of looking at two species of particles. So we've been doing experiments with ceramic beads and glass beads, and the ceramic beads are considerably more dense. We like those because we can buy them. We buy buckets of sandblasting beads, you know, and they're cheap and they're fairly uniform in size, and you can buy them in different sizes. And the ceramic ones are like on the order of twice the density of the glass, which are about twice the density of fluid. So the time scales are really nice in terms of separation in these you know, with the right viscosity oil. We have good time scales, and we can color the ceramic beads in one color. We have some experiments where one is blue and the other is red, and you can get the glass beads opaque or transparent. So there's a lot of things you can do with different colors, and we've been playing with those and trying to figure out, you know, what's the right contrast. You get some interesting optical illusions if you use transparent beads for the one on top, because sometimes you think that the heavier ones are on top because you can see them better, but they're not. And so, you know, we've had some fun with that. So I would say the work is still, I would say, at the preliminary phase, but it's sort of the thing you have to do with multi-species. Now we could try to color individual beads, different colors, to do individual particle tracking. We haven't done that. Let me just say that to do one run of these experiments takes probably on the order of an hour or two, because you have a lot of cleaning up, a lot of prep that you have to go through, and a lot of purchasing of beads and oil, you know, and these are young students who may be less inclined to clean as
You could
as
see
I
that.
would. So,
See that opening and closing the door took a millisecond on the movie. You know, it was
yeah.
fast, so.
Yeah, but the actual experiment, by the way, these experiments that I showed you, that's not real time, that's sped up.
So,
Because,
that's what they said.
right, because it actually, I mean, it takes, you know, depending on how high density a slurry you're working with, it could take, you know, 15, 20 minutes for this thing to slide down the slope. Or it could just take a few seconds. It depends on what you're putting in. Yeah.
Very good. So for Andrea and all the speakers today, thanks.
Yep.